hardware efficient error correction. Okay, great, no worries. So before I jump in, I just want to take a brief moment to acknowledge all of my colleagues at the AWS Center for Quantum Computing here. All of the work I'm going to be talking about today was highly collaborative, and pretty much everyone here at the center was involved and contributed to it in one way or another. So I want to make sure to give credit there. Specifically, the work that I'm going to be talking about today is covered in these 3 papers that we put out just in the last couple of months of last year. I'm going to, or I should say, so there are 2 experiments and a theory paper as well. I'm going to mostly focus on this experimental paper in particular, but I'm going to bring in aspects from all 3 of these papers during the talk. Okay, so since this is going to be a talk about error correction, I thought a nice way to start off would just be to remind everyone just how far it is we have to go to get to useful applications of fault-tolerant quantum computers. So where we are currently is, today's quantum computers tend to have between tens and hundreds of physical qubits and error rates on the order of 10 to the minus 3. Whereas for useful applications, things like chemistry, optimization, machine learning, and so on, we estimate that we're probably going to need between hundreds and thousands of good logical qubits, where by a good logical qubit, what I mean is a qubit with an error rate of, say, 10 to the minus 10 or better, ideally. The specific error rate is going to depend on what kind of applications we're interested in. So this is quite a large gap between the 2 of these. We have 7 orders of magnitude or more potentially that we're going to need to overcome in order to get to useful applications of quantum computers. Now, the nice thing is, of course, we have a solution to this problem in principle, and that's quantum error correction. But a lot of what this talk is going to be about is the practicality of that solution and finding more efficient paths to potentially cross this chasm. So I expect this is an audience where I don't really have to say too much to motivate quantum error correction, but in order to draw some contrast later with the somewhat unique approach that we've taken to it, I do just want to spend a minute to put up a sketch of the main idea here. So as many folks in the audience, I'm sure know, the basic idea here is that in order to protect quantum information using error correction, what we want to do is somehow redundantly encode a logical qubit across many physical qubits, such that even if these physical qubits suffer from noise and errors, the logical information is still preserved and maintained. And so in this little cartoon that I have here, the physical qubits are represented by these 2-level systems in the gray boxes, where the red line indicates that these qubits are noisy and error-prone. And by combining many of these together, we hope to obtain a good logical qubit with a much, much smaller error rate. So the last several years have been quite exciting in terms of proving out this basic idea in experiment. We've seen devices in trapped ion systems, superconducting circuits, and neutral atoms as well, all demonstrate kind of the basic core ideas of quantum error correction, from small codes to logical memories beyond the break-even point, where the logical lifetimes exceed the physical lifetimes of the constituent elements, and even basic fault-tolerant logical operations between small codes as well. So it's been an exciting couple years of quantum error correction, and we're sort of well on our way now to realizing this vision. But even so, I think it's important to not lose sight of just how far it is we have to go. And in particular, we still have to cross this chasm of at least 7 orders of magnitude reduction in error rate. And practically speaking, I think the important question to keep in mind as we think about doing that is exactly how many physical qubits that it is we're going to need in order to construct a good logical qubit. So many experts would agree that the answer to this question is we're going to need a lot of physical qubits to build a good logical qubit. And that makes this, even with these recent experimental demonstrations, still a daunting prospect. To be a bit more quantitative, I just wanted to walk through an example here with the surface code, one of the most popular error-correcting codes, just to give a sense of how many qubits we're talking about for useful applications with quantum computers. So here's a schematic of the surface code shown here on the left, and to estimate how many qubits we're ultimately going to need to run useful algorithms, we can use this expression on the right, which is an approximation for the logical error rate of an encoded surface code qubit. This logical error rate relates to the physical error rate, the threshold of the surface code, and also the code distance, roughly the size of the code. So what we can do is we can take this expression and plug in some reasonable numbers. and ask how many qubits we'll need to get to these kind of good logical error rates. And something like 600 physical qubits or so, we might expect, is the number we're going to need to get to error rates of, say, 10 to the minus 10. But we shouldn't forget that when we want to actually run useful algorithms, we're going to need between hundreds and thousands of these logical qubits. And so that means at the very least, we're going to be needing millions of physical qubits with this kind of approach. This, of course, is several orders of magnitude more than we have in our systems today. So this is quite a daunting path that we would have to proceed along. And so I think it begs the question, are there more efficient approaches that we can find, ways that we can get to good logical qubits and useful quantum algorithms without such daunting overheads? And that's really what we've been interested in and have focused on in our recent work. Okay, so that brings me then to an outline for the talk. I'm going to start off by telling you about bosonic quantum error correction, which is really kind of our secret sauce, if you like, of the approach that we think is going to give us a more efficient path to good logical qubits. And then from there, I'm going to tell you about an experiment that we did recently where we built a logical memory using this bosonic error correction. I'll walk through how that memory can correct different kinds of errors and talk about its performance. And then at the end, I'll wrap up and talk about some future directions. So starting then with this bosonic error correction, let me jump in. So the basic idea of bosonic error correction is shown here. In contrast to this kind of standard qubit-based error correction that I was just talking about, where we're redundantly encoding a logical qubit across many distinct physical qubits. In the case of bosonic quantum error correction, what we're actually going to do is encode a qubit within some quantum harmonic oscillator or a bosonic mode. Something like, for instance, an electromagnetic or a mechanical resonator. And so in both of these two approaches, the core idea is more or less the same. We want to somehow redundantly encode quantum information in a larger Hilbert space. In the case of the standard QEC approach, that larger Hilbert space is the joint Hilbert space of many distinct physical qubits. But in the bosonic QEC case, that larger Hilbert space is the infinite dimensional Hilbert space of a quantum harmonic oscillator. Now, what's particularly nice about this bosonic QEC is that even with just a single physical element, this one oscillator here, with this approach, we already have the ability to begin correcting some errors. And so that already hints that this kind of approach is going to be potentially more hardware efficient for us because we need only one physical element to start handling and correcting some of the errors. Now, much like the standard approach to QEC in the last several years, we've seen a lot of exciting experimental progress when it comes to bosonic quantum error correction as well. So here on this slide, I'm just doing a very brief survey of some of the recent results in the field. Some examples of bosonic codes are cat codes, binomial codes, GKP codes. There are many others as well, but here are just some of the main ones, and I'm listing some of the recent experiments for these as well. What's notable about some of these experiments is that a number of them have approached or exceeded the break-even point where the lifetime of the encoded qubit exceeds the coherence time of the bare oscillator in which it's encoded. So this is some really exciting progress as well. Now, I won't get into the particulars of all of these codes, although I will come back and talk about cat codes specifically at length in a little bit. But here, rather, what I just want to emphasize in showing some of these results is that all of this prior work has a common theme, which is that with just a single bosonic mode, we're already able to correct or suppress certain types of errors. So this is a compact and efficient approach to error correction in terms of hardware. Now, unfortunately, this isn't the whole story for bosonic quantum error correction in the sense that we don't generally expect to be able to get all the way to a good logical qubit with, say, 10 to the minus 10 error with just a single bosonic mode. That is to say, we expect that even with this bosonic quantum error correction, the encoded bosonic qubit is probably still going to have some residual errors that are going to need to be corrected. And so how we handle that is we're going to take these bosonic qubits and then subsequently concatenate them with a standard qubit error correcting code, say something like the surface code. And in that case then, by combining together sufficiently many bosonic modes, we can correct all of these residual errors and reach arbitrarily low logical error rates. So we can recover, again, this good logical qubit. And I think what's important to emphasize here, though, is that even though we still have to combine together multiple bosonic modes, we have gained something in the process of using this bosonic quantum error correction. Namely, because we have already corrected some errors at the physical level of these bosonic modes, this second layer of QEC can be much more simple and efficient. Essentially, we have fewer errors to worry about, so we're going to be talking about smaller error-correcting codes and improved performance when it comes to this second layer of error correction. At least that's the hope and the promise of these bosonic codes. So where does our work fit in within this picture? Well, what we wanted to do is build on all of these prior experiments that I showed in the previous slide that really demonstrated this kind of bosonic error correction with a single mode. And we wanted to take then, for the first time, multiple bosonic qubits and combine them together and do this outer layer of error correction to really kind of test and probe this premise that it's a path to more efficient logical qubits. And so that's what I'm going to be focusing on, the experiment that we did to try and realize this in this talk. Okay, so before going on from here, maybe let me pause and ask if there are any questions, I suppose either from Zoom or in person here. Let me turn the volume up. Okay, I'll go ahead and proceed. So I wanted to, oh, sorry, there's an echo. Let me turn this off. Okay. Okay. So let me go ahead and give you just an overview of the experiment that we performed to realize this concatenated bosonic quantum error correction that I was describing on the previous slide. So here's a depiction of the experiment that we did. We realized a superconducting circuit device composed of multiple bosonic modes to realize this concatenated error correction. So I'm showing here on the left a schematic of the device, and on the right, this is a layout of the actual device itself. What's good to note first off at a high level in this device is that these different blue circles here in the schematic on the left, these are the multiple bosonic modes that are present in the device. And if you look at the layout on the right, these bosonic modes are represented by these blue squiggly lines. These are two-dimensional coplanar waveguide resonators. They're electromagnetic resonators that are going to be the bosonic modes that we'll use in our experiment. What I want to do now then is zoom in on this schematic of the device and sort of start to break down what's happening here, just a very high level to begin with, and then I'll dig into some of the details later on. So when it comes to qubits, we have two types of errors that we're going to have to worry about correcting. We have bit flip errors that will map 0 to 1 and vice versa, and phase flip errors that will flip between plus and minus. And if our goal is to build a good logical qubit, we need to find ways, of course, to correct both types of errors. And so I want to step through how, in this device, we're going to take care of correcting these different kinds of errors. So first, just zooming in on a single bosonic mode, this one blue circle here, we're going to use a bosonic error correcting code in order to effectively correct the bit flip errors in our system. So in particular, we're going to use these so-called bosonic cat codes to take care of the bit flip errors. And so once we've implemented this cat encoding, we'll no longer have to worry about bit flip errors in our system. Then, once those are taken care of, we're going to combine multiple ones of these bosonic cat qubits together into an outer error correcting code. This is this concatenation step that I mentioned before. And this additional layer of error correction is going to be what we're going to do to correct the remaining phase flip errors in our system. In our particular case, the error correcting code that we'll use for that purpose is just a simple repetition code. So again, I'll come back and explain the details of both of these steps in just a moment, but the point here I just want to highlight is that between these kind of two layers of error correction, the bosonic code on one hand and the repetition code on the other, we're able to correct both kinds of errors, leaving us with a good logical qubit at the end of the day. Okay, so let me start by digging in first to how we correct bit flip errors with these cat qubits. And so in particular, I'm going to zoom back into just a single bosonic mode within this device and look at how those errors are suppressed. So what are these bosonic cat qubits that I'm talking about? Well, these are examples of bosonic quantum error correcting codes where information is encoded within superpositions of coherent states within some quantum harmonic oscillator or a bosonic mode. In particular, the coherent states are these plus and minus alpha states, which have mean photon number alpha squared. So specifically what we're going to do is we're going to choose to define the 0 state of our qubit as this plus alpha coherent state. and the one state of our qubit has this minus alpha coherent state. For any of those who aren't familiar with these bosonic codes or these kind of 2D plots that I'm using to represent the state of the system, I think an analogy to perhaps more familiar system is helpful. So we can think, since we're talking about simple harmonic oscillators, we can think of these bosonic systems as like a pendulum. And then these plots that I'm showing here, these Wigner plots, are essentially plots of the pendulum's phase space. And so you can think of these plus and minus alpha coherent states as essentially two different states of a pendulum, where it's at the maximum of its swing just in one direction or the other. So with this definition then, here's the cat-qubit block sphere. As I said, we have the 0 and 1 states as the plus and minus alpha coherent states. And that means that the plus and minus states of these qubits are these even and odd superpositions of coherent states called cat states. And that's where the name of cat-qubits comes from. Now, what's really interesting about cat-qubits, and the whole reason we were inclined to use them, is that they have very special noise properties. In particular, the probability of a bit flip error within these cat-qubits is exponentially suppressed. The intuition for this suppression is that errors that act on your system tend to act locally in phase space. And so the probability of some error starting you in this plus alpha coherent state and then mapping you all the way to the other side of phase space to this minus alpha coherent state tends to be very strongly suppressed. And mathematically, you can show that for realistic noise models, that suppression is in fact exponential. And so this is really the property that we want to go after and we want to realize in experiment. Because if we can exponentially suppress one type of error, then we don't have to worry about it anymore, and we'll just have to worry about the other error. So speaking of the other error, these phase flips, unfortunately these do not possess an exponential suppression in these cat-qubits. Unfortunately, we actually see a linear increase in these phase flips as the photon number of these cat-qubits grows. But nevertheless, this kind of linear versus exponential trade-off we think is still a favorable one that we'll be able to exploit so that we still don't have to worry about these bit flip errors. The other thing I should say about these cat-qubits is you'll often hear folks talk about them as noise-biased qubits. We can define the noise bias as the ratio of the phase flip to the bit flip probabilities, where using these expressions above, in the case of cat-qubits, this bias grows exponentially as well. And so it's really, if you like, the presence of this noise bias that is going to make this outer layer of error correction more simple and more efficient, and is going to lead to the practical benefits that I was talking about at the beginning of the talk here. So it's important to say that this exponential suppression of errors or exponential noise bias doesn't just come about for free. We do have to do a little bit of work for it to achieve it in experiment. And what I mean by that is if I just initialize some bosonic mode in a coherent state, here I'm showing data from our actual experiment, and I just let it freely evolve doing nothing, what you would find is that errors and imperfections in the system would distort that state, warp it, move it out of the code space. You'd suffer all sorts of problems, and this would undermine the kind of exponential suppression of bit flips that we would like to achieve. And so what you need to do to actually realize this exponential suppression is you need to find some mechanism that actually lets you confine the system to this cat code space. So some kind of stabilization that prevents errors from dragging it outside of that code space. In our experiment, I'll talk just briefly about how we can realize that kind of stabilization. We do so following some of these prior works by designing an engineered dissipation process in order to stabilize the cat-qubits. The basic idea is that we're going to couple each mode housing a cat-qubit to an additional bosonic mode that we call the buffer mode that is a very lossy mode, so very strongly coupled to its environment. And then the coupling that we engineer between this buffer mode and the cat mode is shown here. This is a nonlinear coupling where pairs of excitations from this cat-qubit can be exchanged with a single excitation in the buffer mode. And if you combine this coupling with the fact that the buffer mode itself is very lossy, what you find is that the net effect on the cat-qubit is that it essentially loses photons to its environment in pairs. And this kind of two-photon loss, it turns out you can show, is exactly what you need to stabilize the state of your bosonic mode to this cat-qubit manifold. So the takeaway here at the end of the day is that in an experiment, essentially we can flip a switch in order to turn on this interaction here, and then we'll realize this stabilizing mechanism that should give us this exponential suppression of bit flips. Yeah, question?
So before having this buffer mode, what is the value?
Yeah, what's causing these kind of effects?
Yes.
Yeah, so the question for those on Zoom, maybe who can hear it, is what's causing these kind of distortions? If I had to write down a Lambdatian for the system, absent this stabilization, what would I need to write down to explain this? There are a couple of different contributions. So you'll have typical noise processes for bosonic modes would be things like single photon loss and dephasing. These are dissipative processes described by jump operators A for single photon loss and A dagger A for dephasing. You'll also generally have nonlinearities in these modes. So these are Hamiltonian terms that will act to cause distortions in this space. The typical one that you might have would be a Kerr nonlinearity. That Hamiltonian is A dagger squared, A squared. And so all of those kind of imperfections we do see in our experiments, and this is what we believe is causing this distortion here.
And by adding this buffer mode to
So those mechanisms, if I were to write out the proper master equation I would need to model the system, I would still include all of those terms. We're not doing anything to suppress their strengths. But the idea is we want this dissipation or this the stabilization mechanism to be kind of the dominant effect in the system. So the strength of this dissipation should be sufficiently larger than all of these kind of spurious processes. And when that's the case, despite their presence, you still have the system stabilized to this cat code space. And so making sure that, for instance, this coupling strength that realizes this stabilization is sufficiently large to protect against these processes, and that the spurious processes themselves are small enough is one of the key challenges of this experiment.
Can I maybe ask a follow-up? So does the dissipation kind of also suppress the coherent error due to nonlinearity, like a Kerr term?
Indeed, it does. So what you would normally expect from a Kerr term is actually pretty nicely illustrated here. If you start in some coherent state, a Kerr term will act to shear it and spread it out in phase space. But this dissipation essentially prevents you from leaving this code space in the first place. And so in the presence of this dissipation, Kerr essentially acts as the identity on the cat qubits. So Kerr in particular doesn't really have an effect on the cats. This is distinct from other kinds of imperfections like single photon loss that even in the presence of this dissipation will still lead to errors on the cat qubits, phase flip errors in particular. So the point is not that with the stabilization we don't have any errors, but just that ideally one type of error, the bit flip errors, should be exponentially suppressed. And indeed, when we look at the behavior of our cat qubits in experiment, we do see this exponential suppression when we turn on the stabilization. So what I'm showing in these plots are the bit flip and phase flip times of our cat qubits as a function of the cat photon number. And the 5 different lines that you're seeing in each plot correspond to the 5 different cats that we have in our full experimental device. And so we can see, as desired, the bit flip times are growing exponentially with photon number, which is great. That means that now we're not going to have to worry about these bit flip errors. But the phase flip times have this kind of expected 1 over alpha squared reduction. So we're still going to have to find a way to correct these phase flip errors. And that will bring me then to the next part, the repetition code that we use to handle them. But before getting to that, I wanted to just briefly flash up some additional technical points. I've sort of glossed over a lot of the nitty-gritty details that were necessary for us to grapple with to get good performance out of these cat qubits. I'm not going to go into these details here, but I did just want to briefly flash them up in case anyone in the audience was interested. You can ask me questions about them at the end of the talk. But just briefly, we had to do a lot of work, for instance, to make sure that the coherence times of these bosonic modes that house the cat qubits, that those stayed very high, even in the presence of the strong engineered dissipation, and that these kind of spurious nonlinearities, like Kerr terms, did not become too large in the presence of the nonlinear interactions we were trying to engineer. And we also had to make sure that we didn't accidentally activate spurious Hamiltonian terms or processes that would degrade the performance, and had to do a lot of work modeling the system to make sure that wasn't the case. So here again, I won't go into details, but if you're interested in any of these aspects, please feel free to ask. Okay, so we've talked now about how we can suppress bit flips with the cat qubits. Let me now move to how we can correct phase flips using this outer repetition code. So here again, now I'm going to zoom out from just one single bosonic mode, and I'm going to consider now a chain of 5 bosonic modes that we had in our device combined together into a repetition code. Yeah.
So finally, when it's eventually what you do, what is the
The actual bit. Yeah. So these are actually measured bit flip times. So just, to read off some numbers here, depending on the photon number we have, these range, small photon numbers on the order of milliseconds to tens of milliseconds. I'll show some data later. They actually extend up to about a second or so in some of our better devices. But as we'll see, when we combine multiple ones of these bosonic modes together and do our repetition code error correction, there are going to be additional sources of bit flips not present in these single cats that we're going to have to contend with that are going to limit the performance of the bit flips in the repetition code. So I'll talk about that at length and give some numbers for what that limit is and how well we perform. But it's worth pointing out that by themselves, these cat-qubits are really very good at exponentially suppressing bit flips. When we're talking about like a second scale bit flip time, if you compare that to like a microsecond scale for an error correction cycle, it's like a 10 to the minus 6 probability, something like that. So by themselves, these cat-qubits are great. It's everything we kind of wrap around them that makes the problem a little bit more difficult. Okay, yes, so as I said, now let's turn to the phase flips and how we can correct these with a repetition code. Before jumping into that, though, I just wanted to briefly highlight why it is in this context we can get away with a repetition code, in contrast to, say, something like a surface code that I showed before. And intuitively, the idea here is that with a standard surface code, you can think of the two directions, the length and width of the surface code, as corresponding to the ability of that code to correct bit flip and phase flip errors. But in our case, all of the bit flip errors are effectively handled. And so now we don't actually need any redundancy in this direction. And so if we take away that redundancy, we're essentially just left with a one-dimensional chain, if you like, a repetition code. And in fact, indeed, the observation that you could combine these bias noise cat-qubits with a repetition code to get a good logical qubit, that was first proposed in this theory paper here. And it's worth emphasizing that this is really kind of the whole benefit that we're expecting from these bosonic qubits. In particular, the fact that we don't have to worry about a surface code and now can get away with just a repetition code is great for a number of reasons. First, that it just means a reduced overhead to get to a good logical qubit. We've gone from a two-dimensional array just to a one-dimensional array. But even beyond that hardware overhead reduction, the repetition code also has a higher threshold and lower connectivity requirements. And so all of these factors together make this a much more favorable experimental implementation. So this is where these are really the benefits of these bosonic codes. Okay, so let me get into how we actually correct these phase flip errors with our repetition code. So the idea is that we are going to repeatedly measure the stabilizers of the repetition code. The stabilizers are shown as these gray triangles here. These are these XX two-body Pauli operators on adjacent qubits. These stabilizers anti-commute with the phase flip errors on the bosonic qubits, so that when a phase flip error occurs on one of these cats, if we're measuring the stabilizers, we'll see their value change. And so we know when an error has occurred, and by looking at which stabilizers have had their outcomes flipped, we can infer where that error has occurred and go in and correct it. Now, as is typically done to actually measure these stabilizers, what we're going to do is introduce ancillary qubits. And then the measurement works by performing entangling gates, here C0 or CX gates, between the ancillary qubits and the data qubits, and then measuring the ancillary qubits. What's important to emphasize in our case is that for the ancillary qubits, we're not actually using cat-qubits, but rather we're using standard transmon qubits. We did that mainly for practical purposes. It made the experiment much easier to implement, much more practical. In particular, as I'll show, implementing these kind of entangling gates is comparatively much easier when you use transmons instead of cats. But there are some important consequences and complications that arise from these from the use of transmons. So, we get a win practically, but there are some additional complications we have to pay attention to. In particular, we have to worry about the possibility that these transmon qubits, which don't have any kind of error suppression on them, we have to worry that perhaps if we have errors in these transmon qubits, those could propagate through the entangling gates and potentially cause bit flip errors on our cat qubits. If that were to happen, that would be a problem for us because this repetition code doesn't have any way of correcting these bit flip errors. And so a real challenge then of realizing this repetition code was finding a way to implement these CX gates that was noise biased. That is, to make sure that errors in the transmon are not inducing bit flip errors in the cat qubits. And so for the next couple slides, I'll just dig into how we realize these gates and how we try to prevent this kind of damaging error propagation from happening. So the basic idea and the way we realized these CX gates was actually originally put forth in these couple of papers from the Yale group, and there are two key ideas at work here. So the first is that the sort of native dispersive interaction that you get between a bosonic mode and a transmon, that is the interaction that just falls out when you couple these two systems together, is this dispersive interaction here. And as we'll see in a second, this interaction just naturally generates a CX gate if you just freely evolve under it, which is very convenient and one of the reasons why we wanted to use transmons in the first place. The other important ingredient in this gate, though, is that we're going to choose to, rather than operating the transmon in its G, ground, and first excited state E, we're going to choose instead to operate it in its ground and second excited state F. And this choice is going to be responsible for giving the gate robustness to errors in the transmon, again, as I'll show in a moment. But let me first just step through how this gate works. So in the case where the transmon is in G, if we look at this Hamiltonian, it acts trivially if the transmon is in G, and so the system doesn't evolve, it just stays as it is. However, in contrast, if the transmon is in the state F, this term in the Hamiltonian here is going to induce the cat mode to rotate in phase space at a rate chi. And so it'll evolve like this. If you wait for an appropriate amount of time, this will map the plus alpha state to the minus alpha state, effectively realizing a bit flip in the cat from plus alpha to minus alpha. And so then we, from this Hamiltonian, we directly get the desired CX gate behavior, where if the transmon's in G, nothing's happened, but if the transmon is in F, we get a bit flip from plus alpha to minus alpha. So that gives us the CX gate. But as I said, we don't want just any CX gate. We want to make sure that somehow the CX gate is robust to errors in the transmon so that they don't induce bit flip errors in the cats and compromise its noise bias. And in order to realize that, we need a special condition in this Hamiltonian here, where this rate chi E is approximately equal to this rate chi F. When this so-called chi matching condition is satisfied, what one can show is that this gate becomes robust to transmon T1 decay errors, which are the dominant errors afflicting the transmons. So to see this robustness and how it works out, let's consider the case where maybe I initialize the transmon in the state F, but it suffers a T1 error, and so it decays to the state E. In that case, what happens when we evolve under this Hamiltonian is now the mode will rotate at the rate chi E, which might not be exactly equal to the rate chi F, but it should be close enough so that the cat approximately undergoes the desired rotation. What happens then is if we turn back on the dissipative stabilization to return this mode to the cat code space, this state will be dragged back to the ideal minus alpha state. And so the point being that even if we have a T1 decay error in the transmon occurring, we still successfully realize this rotation from plus alpha to minus alpha. And so this gate should be robust to transmon T1 errors, at least from the perspective of the cat and its bit flips. Now, that said, this gate is not going to be robust to higher order error mechanisms, things like double decay in the transmon, where you decay first from F to E, then E to G. And these sort of higher error order or low probability processes are ultimately going to place a limit on the bit flip rate of the cats. That's going to place a limit in turn on the performance of the repetition code, as I'll show. But at least to leading order, we should be protected from the dominant errors in the transmons. So to show you what this gate looks like in action in the experiment, here I'm showing some data of stepping through in time. So here's a state of the cat mode before the gate, after the gate, and then after this dissipative stabilization is applied, and for the three different transmon states. And we can see that as desired, when the transmon's in G, the cat starts in plus alpha and again winds up back there, whereas for the states E and F, it successfully completes this rotation from plus alpha to minus alpha. And the fact that these plots look very similar between E and F is what indicates to us that we should have robustness to transmon T1 errors. More quantitatively, we can look at the performance of this gate in terms of the bit flip times of the cat during the course of this gate. So in particular, what I'm plotting here are the cat bit flip times as a function of alpha squared. And the different lines correspond to, here in black, this is just an isolated cat-qubit on its own, so no CX gate involved. And these gray and blue lines, in contrast, correspond to CX gates of different types on the cat. So in particular, this gray line, this is like a very naive implementation of the CX gate that only uses the GE levels here, and so has no robustness to transmon errors. And you can see that as a result, there's a big drop in bit flip times due to this lack of robustness. In contrast, if we use this implementation I was just describing that uses the G and the F states, that's shown here in blue, we recover a good chunk of the bit flip times, but we still don't get all the way to the performance of the isolated cat. In particular, as you can see here, this bit flip time is starting to plateau. This is due to these higher order transmon error processes that are ultimately going to place a constraint on how high these bit flip times can be. In our experiment, that limit is just a couple of milliseconds, it turns out. But this is, nevertheless high enough for our purposes in order to show, some interesting performance. Yeah.
So, like during this implementation, do you do any sort of post-selection or no?
No, so no post-selection is done here. So this is an entirely deterministic gate. Of course, what happens if the transmon decays, or I should say, in the course of measuring syndomes, we're going to prepare the transmon in some superposition, perform these entangling gates, and then measure the transmon. Of course, if the transmon has an error during that process, the syndrome measurement is liable to give us the wrong information. And so we have no robustness in terms of those measurement outcomes to transmon errors, but that's okay. You can always repeat those measurements and try to ascertain that syndrome measurement in the next round. But the main thing we have to worry about is that making sure the cats don't have bit flip errors, because if the transmon errors propagates to that, there's nothing that we can do about it. Let's see, any other questions about the gate at this point? How can we tell in the experiments that we've seen those decay processes? Yeah, so we actually have in this experiment a readout of the transmon where we can separately distinguish between G, E, and F. And so what will happen is that as we're going through and performing these gates, if we've initialized the transmon in F, ideally it should stay there. And then if we subsequently read out the transmon and find instead that it's in the state E, we can infer that a decay has happened at some point during the process. The fact that we can actually distinguish separately between these three states, it's by default, most folks will just operate the transmon using only the GE states. You have to work a little bit harder to be able to measure and separately tell these three states apart. That turns out to be a nice feature for us for a number of additional reasons, actually. One being, for instance, that if you have a decay from F to E, and now you can tell that the transmon is in the state E later, that you've learned then that an error has occurred on the transmon, and you can actually treat that, if you like, as a sort of erasure error, where you know that essentially the state of the transmon was lost. And this is something we incorporate into our decoding in order to perform, to improve the performance of the logical memory. So just an aside, but yeah, in answer to the question, we just have a measurement that can directly distinguish these three states. Okay, so as I said, really the main ingredient we need for this repetition code error correction is this CX gate. And so this is our realization of that. So now we're all set in terms of being able to do this repetition code error correction. Before moving on, though, and talking about performance, here again, I wanted to just briefly flash up some technical details that turned out to be very important in getting all of this to work. Here again, I'm not going to spend too much time, but ask me after the talk if you're interested in any of this. The first one is actually what I was just mentioning. The fact that we use this GF encoding for the transmon means we can detect T1 errors and treat them as erasures. And this is helpful for improving the performance of the repetition code. Some other important aspects that we had to think about. We wanted to make these dispersive couplings that generate the gate tunable so that we could turn the gate on and off at will. So we developed tunable couplers for that purpose. And also how we realized this kind matching condition is kind of interesting. We did it via a very careful frequency targeting or frequency relationship between the transmon and the cat mode. So here again, ask me if you have questions about this, but for the time being, I'll just move on now and now tell you about how our logical memory wound up performing then. So we've seen how we can correct bit flip and phase flip errors. Let's start by looking at the logical phase flip probability. So this is going to be the probability of an error after we've done this repetition code error correction. So to what extent does our repetition code actually correct these dominant phase flip errors in the cat qubits? So what I'm showing in this plot here is the logical phase flip probability per error correction cycle as a function of the cat photon number alpha squared. This purple line here is the logical error of the full distance 5 code, whereas the blue and red lines are logical errors for distance 3 subsections of that distance 5 code. What's neat about plotting the logical error as a function of this parameter alpha squared is that, as a reminder, this phase flip rate is proportional to alpha squared. And so, in effect, what we're doing is then plotting the logical error as a function of the physical error. And so what that means then is you can essentially look at this plot and just then directly read off from it that this repetition code is operating below threshold, because this d equals 5 line is falling below the d equals 3 lines. And it also has a steeper slope as well, telling you that errors are being suppressed more effectively. And so indeed, we have the repetition code operating as desired. It's below threshold. We're able to successfully correct phase flip errors in our system. On the other hand, what about these logical bit flip errors? So as I mentioned, the repetition code has no redundancy to these bit flip errors. And so we generally expect that as we add more and more cats to the system, the probability that any one of them is going to suffer a bit flip error is going to increase. And so in order to have a low logical bit flip error probability, you just need to make sure that all of the cats in the system and all of the gates have very low bit flip probabilities themselves. And so indeed, this is what we see here when we look at the logical bit flip probabilities. Here again as a function of alpha squared. Initially, we have this suppression of bit flip probabilities as alpha squared is increasing. That's thanks to the increasing protection of the cats. But eventually, these bit flip probabilities saturate as the cat qubits, as the bit flips become limited by these additional error mechanisms from the transmon during the CX gates. You'll also notice that the logical bit flip error for the distance 5 code is higher than that for the distance 3 codes. That's again just because the repetition code doesn't provide any protection against bit flip errors. So the more cats we have, the more probable that one of them is going to have a bit flip. But even so, I think it's worth emphasizing that, say for this distance 5 line here in purple, this is essentially the sum of bit flip errors across all of the 5 different cats present in the system, as well as the 8 different CX gates in that case that we have to do to measure the syndromes. And so the fact that that logical bit flip error is falling below 1% is really a testament to how much noise bias there is in the system and how low the bit flip rates are themselves. So if we put these two plots side by side, the logical phase flip and the logical bit flip, we see the phase flip is increasing with alpha squared because the physical phase flips are become more probable with alpha squared, whereas the bit flips are decreasing with alpha squared. And so that means then that if we look at the total logical error rate, it's going to be optimized at some finite value of alpha. So here's a plot then of the total logical error rates for both the distance 3 and distance 5 codes. And you can see, indeed, they have these kind of curved shapes where there's some minimum at different values of alpha squared. And I pulled out these minimum values here on the right. So we see that for the distance 3 code, on average, that minimum error is about 1.75%, whereas for the distance 5 code, it's about 1.65%. So I think the what's important to emphasize about this is the fact that these logical error rates are even comparable is really only possible because of the noise bias in the system. If you took qubits without noise bias and made a repetition code with them, you would necessarily find that the larger the code got, the higher the total logical error would get. So the fact that these things are even comparable is really only enabled by the noise bias. So we were pretty excited to see that borne out in the experiment. Okay, so let me look at the time here. I have just over 10 minutes left. Let's see, should I leave a couple minutes at the end for questions?
I think if you go over 3 minutes, it should be okay.
Okay.
Yeah.
All right, then let me go ahead and spend just a couple minutes on this slide as well. So we also spent some time trying to understand the budget or the error budget for our system. So what are the main contributors to this logical error rate? So that's what's being shown in this plot here. The purple line is the same one I just showed. That's the measured logical error rate. And all these different colored components here are different error mechanisms that we modeled in theory that are summing up and contributing to the logical error rate. And in particular, what you'll notice is that it's these green and red contributions that are really the main things contributing to the total logical error. These correspond to the intrinsic phase flip and bit flip rates of the cat qubits. So what's significant about that is that, in contrast, these blue contributions, these are bit flip errors from the CX gates. Those are actually not the main thing limiting our logical error here. So though I spend some time emphasizing how transmon errors ultimately do limit the bit flip times of the cats in these CX gates, turned out not to be the main thing limiting the performance of our experiment here, though down the line it will ultimately pose a fundamental limit. In terms then of the individual cat performance, I've written out some numbers here in terms of what we expect of the phase flip and bit flip probabilities for these cats at the optimal points. They're around 6% and 3 times 10 to the minus 3. So we see some noise bias in these cats at this particular choice of alpha squared, around 1.5. And so, in order to improve the performance of this repetition code in the future, the main thing we'd want to do to start is find ways to improve the phase flip and bit flip rates. And we think there are a number of straightforward ways to do that. For instance, our error correction cycle duration was about 3 microseconds. That's the time it takes to perform the gates and measure the syndromes. That we think should be pretty easy to reduce, and so we provide a straightforward path to reducing some of these errors so that you could further drive down this total logical error. Okay, so that covers the performance of the logical memory and experiment. Let me maybe pause here and ask if there are any questions on that before moving on and starting to wrap up.
Can I ask maybe a bit of a naive question? If I'm understanding correctly, like in the previous kind of error benchmarking, like those are with respect to the cycle. Like, is there a sense of making a comparison with respect to the logical gate time? Like, do you have an estimate of, or this is more like a memory? Like, I guess I'm a bit confused about.
Yeah.
Like, it makes sense to talk about like the memory time itself being extended, but like, do you also have some expectation of like how well it will behave if once you kind of want to do logical gates?
Yeah, so these probabilities that I'm quoting for the total logical error and as well as for the individual phase flip and bit flip errors, these are probabilities per error correction cycle.
Right.
When it comes to doing logical gates, suppose you wanted to do gates via some construction like lattice surgery, then you're generally going to need multiple error correction cycles in order to perform a logical operation. Say D error correction cycles when you have a distance D code. And so naively then in that case, your error in your fault tolerant gate would be something like D times this epsilon L. Although in the specific case of the repetition code, that's not necessarily true. You could, for instance, if you wanted to do a C0 gate between 2 repetition codes, you could actually do that transversely, even in a 2D system, because these are, the repetition codes are each only one-dimensional, and so you can just do C0s directly between the pairs of the qubits. So in terms of fault-tolerant logic, there are actually some ways in which the repetition code can be more efficient than like lattice code with the lattice surgery with the surface code. But roughly speaking, you can understand this epsilon L is at least proportional to the kind of logical error rate of fault-tolerant operations.
Right, and like, does it even make sense to make a comparison with the Bearcat? Like, it's always going to be worse again as expectation because you're not doing repetition.
Yeah, so directly, I mean, you can look at so these, if you like, are the Bearcat phase flip and bit flip rates. Obviously, this phase flip rate of 6% is not great, but or I should say, in isolation comparing to like other gates or other platforms, you look in this and say this isn't great. But the reason we're not so concerned about this is because all we care about is that this phase flip rate falls below the repetition code threshold, which is itself like 10 to 20%, something like that. And so, so long as it's below that threshold, we don't actually care what its value is because we can just make the code larger, and that logical phase flip probability should go down. So that's really why I haven't emphasized comparing directly the physical to the logical error rates here. We can, you can calculate what the corresponding logical lifetime in terms of, say, microseconds would be and compare that to the physical lifetimes. In our system, what we find is that the logical lifetime is better than the worst physical lifetime in the system, but it's not yet better than the average physical lifetime in the system. So in terms of, if you wanted to make a claim about break even or something like that, it's not quite there yet. But yeah, I think it's more instructive in this case because you have noise bias in these asymmetric errors to think of it a little differently from that, perhaps.
Let me ask a follow-up question here.
Mm-hmm.
So, in the previous slide, you had like slight increase from distance to distance slide, and like there are 2 different like behaviors. Like, one is going up the distance, one is going down the distance.
On this slide here or the previous one?
Like the bit flip and the phase flip that you have, one is going down with distance, but the other one is going up.
Yeah.
You expect the total to go down with distance?
Yeah, so this is a good question. So indeed, because the repetition code does not have any ability to correct bit flips, and as you make the code larger, the logical bit flip probability is going to increase. Eventually, if you keep going, the logical error probabilities are not going to decrease arbitrarily. Said another way, the repetition code is not a good quantum code. It doesn't have a proper threshold because it only corrects one type of error. And so that means that there's going to be an ultimate floor to the logical error that we can achieve with this repetition code. And that's going to be set by the bit flip rates of these cat qubits. Or in our case, these bit flip rates either in isolation or during these CX gates. So what that means is, there's going to be some optimal distance to the repetition code beyond which going further isn't going to be helpful. In our case, for this experiment, it probably was about distance 5 for these parameters. But with some of the improvements that I was mentioning, for instance, faster cycle times or higher coherence times and so on, we expect that the optimal code size would increase and the floor for that error should go down as well. And I can say a bit more about that in just a second. But yeah, indeed, there's a limit to how far you can get with just the repetition code by itself. Okay, then let me take just the last couple of minutes here and wrap up. And indeed, this is directly related to the question that was just asked. So to conclude, I want to just touch on a couple of long-term directions that we're thinking about in terms of improving the performance of these kind of devices. And in particular, I want to focus on this problem that I mentioned earlier, where errors in these ancillary transmons, at least higher order errors, can propagate through the gates and cause bit flip errors in the cats. That's ultimately going to place a limit on the logical error that we can achieve with these repetition codes. And so we need to find some way to deal with that problem if we really want to push down the error floor. So there are two directions we've been thinking about to handle this problem. One is directly finding a way to correct these transmon errors, and another is finding a way to improve these CX gates themselves. So just briefly, the first direction, which we talk about in this paper here, to correct these transmon errors, kind of the most natural and obvious thing you might do is just move from a repetition code to a surface code so that now you do have some redundancy, some ability to correct bit flip errors when they occur in the cats. We don't want to move all the way to a square surface code because we'd like to still preserve some of this hardware efficiency. So what you can do instead is move to a rectangular surface code where you have a very limited amount of redundancy, ability to correct bit flips. But that's fine because the bit flips themselves should already be fairly well suppressed. So you still maintain some of this hardware efficiency, but now you don't have this fundamental limit anymore. As you grow the code, you should be able to suppress errors arbitrarily. I won't get into all the details of what's involved in moving from repetition to surface codes, but maybe just to show one of the kind of high-level takeaways from this work we did about this. This is a plot of the logical memory overhead, so the number of physical qubits required to realize a logical qubit as a function of physical error rates. And here, the different lines, the colored ones, correspond to this kind of setup where we have rectangular surface codes with noise-biased cats, whereas the black line is a reference. This is a case with unbiased noise qubits. So in our analysis, we expect that physical error rates somewhere around 10 to the minus 3 should be realistically achievable in some near future devices. And if we compare that to the case without biased noise, what we see is that this winds up giving us, if you like, either a 5 times reduction in the overhead or equivalently a 10 times reduction in the effective error rate. So the point being here that even though we've now moved back to the surface code, we're still benefiting from the presence of the noise bias in terms of giving us a more hardware efficient approach to error correction. Okay, so this is one way we might be able to handle these transmon errors. The other direction I wanted to mention for how we might go about this would be to, instead of continuing to use these transmon ancilla qubits, we could instead switch to using cat ancilla qubits instead, because of course these cat qubits have suppressed bit flip errors, and so now we shouldn't have to worry about errors from a cat propagating into bit flips on the other cat. Both have their errors suppressed. And this is, I think this is a direction we're excited about because as I was mentioning earlier, the performance of these cat qubits is quite good. So here's some of the data I was talking about before, where we have bit flip times for an individual cat approaching about a second. And indeed, you get almost there with about 4 photons in the cat. So it's really very long bit flip times for comparatively quite small cats. That's pretty exciting. So just to, if we suppose then that we had CX gates between these cat qubits that we could perform that were only limited by the coherence of these cat qubits themselves. So these roughly 1 second bit flip times that you could achieve. If you plug in some numbers here, what you find is that you could reach logical errors on the order of 10 to the minus 5 with a repetition code containing only d equals 11 cats. I think what's remarkable about that is it's a very small overhead to reach such a low logical error. And so, there's a lot of potential appeal here in terms of really leveraging these high performance cat qubits. Now, there's a big caveat here, which is that we don't actually know a way to perform a CX gate between cat qubits that is limited just by the coherence of the cat qubits. There are proposals to implement these gates, but they come with significant additional control error. So you're not really going to be able to get all the way to this performance limit. But I think what this hypothetical illustrates is that nevertheless, these cat qubits themselves are very performant. And so further research into how to implement these gates and optimize their performance will have a lot of practical payoffs in terms of allowing us to have very hardware efficient approaches to getting good logical qubits. And then the other thing I just mentioned about this is beyond just being able to make very low logical errors, there's some other benefits that would come along with this approach and having very large bias. In particular, when you have a really, really large noise bias in the system, you can start thinking about LDPC codes that only require local connectivity. So in contrast to standard LDPC codes that folks have been talking about lately, which generally require non-local interactions, when you have really large noise bias, you actually only need local connectivity. So that would be quite practically appealing. Larger noise bias also comes along with easier decoding, the potential for transversal gates as well. So this kind of path that would allow us to get to larger noise bias has a lot of knock-on benefits as well. Okay, so with that, it looks like I'm at time here. So let me just wrap up. And again, thank all of my colleagues at the Center for Quantum Computing at AWS. Again, this was a very collaborative set of works that we all did. So, I'm here presenting, but really it was everyone on the team that contributed to all this. And here again, the various different papers that I talked about. Yeah, so with that, thanks everyone for your attention, and I'm happy to take any questions.
If there are questions of maybe I'll ask hopefully a quick one, and people have questions like 3 to later. You mentioned that I think during your talk, if you're looking at a single cat, like can have bit flip time up to a second, but somehow when you put them together, like you're susceptible to new processes. Maybe I missed it. Like, can you just give a bit more?
Yeah. So in particular, the processes that I was referring to in that comment are exactly these kind of errors from the transmon propagating to the cats. So to be concrete, I had this plot earlier showing the comparing, if you like, the isolated bit flip times of the cats. Here, this is starting at milliseconds and then going up to tens of milliseconds, and actually this curve keeps going up to around a second. But when we're doing these CX gates for the purpose of measuring the syndromes, it saturates instead just beyond a millisecond. So those are the additional error mechanisms that, in the course of implementing repetition code error correction, sort of constrain the performance of these cat qubits.
And supposedly this can be kind of improved or fixed with other approaches.
Yeah. So this would be the two directions I touched on at the end. So either finding some way to correct these sort of limiting errors, or alternatively finding a slightly different implementation here, so that they're not rising in the first place.
Any questions from the audience? Yeah. Now I guess we're on the hours mark, so give us some over again, and yeah, we'll be here tomorrow.